This is the second of four spring problems. In this one you have a vertical spring. We don't worry about its mass. If we have to calculate it and use its mass, this will change the problem greatly. Whose spring constant is 900 Newton meters is attached to a table and is compressed by 0.15 meters. They want to know what speed can it give to a 0.3 kilogram ball when it's released, and then they will also want to know how high above its original position will the ball actually fly. Let's do the first part. We know that the change in distance, or the displacement, is up. We've got our spring, and we put the little ball on the spring, and we know that the force of the spring is going to eventually make the ball go up, and we know that our applied force is pushing down on the spring. The work here of the spring, if you remember, is equal to 1/2 kx squared. We know that work, energy theorem says work is equal to the change in kinetic energy. So work for a spring is 1/2 kx squared. That's equal to the final minus the initial kinetic energy. There is no initial kinetic energy, so that leaves us with the equation 1/2 kx squared is equal to 1/2 mv squared. At this point, what we can do is go ahead and solve for v. I'm going to go ahead and just put down what v would be. V should be equal to the square root, because both of the halves come off. You divide both sides by m, take the square root, so you should end up with kx squared all over m. We can plug our numbers in, so v would be equal to 900. We take that times 0.150, we square it, and then we need to divide by our 0.3 kilograms for the mass. You should end up with a speed of 8.22 meters per second, and that would be the speed of the ball. For part B, it says how high above its original position when the spring is compressed will the ball fly. So what we need to do is go ahead and do part B. Let's do it to the right side here. Move this up out of the way. And for part B, we now look at the original speed of the ball, okay, down at the very bottom. So it has an initial speed going up. We know that the force on the way down is mg. So when the ball goes up, the force down is mg, and it's got to speed up. Up at the top, here's the ball again. Here's the ball originally. We'll fill it in for the original. We'll leave it empty for the final. The final speed at the top would be 0, and we know that the kinetic energy at the top would also have to be 0. Let's use our work energy theorem. Work is equal to the change in kinetic energy. This time we're worried about the ball. We're not worried about the spring, so we're just going to look at the ball. We know that the work done on the ball is mg times the displacement, and we need to multiply that times the cosine of 180, because my distance that it travels up is opposite of what the force is that's pushing it back down. That should be equal to the final kinetic energy minus the initial kinetic energy. Final energy here is 0, because we know we defined it here from the speed being 0 up at the top. At this point, we know cosine of 180 is negative. We go ahead and put in our mg delta r, and that should be equal to negative 1/2 mv, and that's the original speed, squared. At this point, we notice that our negatives cross off and our masses also cross off. At this point, we are left with the equation the change in displacement is equal to v squared over 2 times g. Let's plug everything in. That would be 8.22. That was the speed of the ball when it left, and that is squared over 2 times 10. And when you get done, then we should end up with our answer. So at this point, the final answer should be 3.38 meters. If we take the numbers that we have and we divide them, so we're going to take 8.22, we'll square the 8.22 and then divide that by 20, you get 3.38 meters. And so that would be the answer that we have for this problem, and that should be the end of the sample problem number 2 with springs.